Hello, my dear warriors. Welcome to the Fastrack series, the revision series for all the JEE and other competitive exam aspirants. So here in the Fastrack Mind Maps and Formula sessions, I give you all the important concepts, the theory pointers, the formulas, and all the important charts, graphs, everything related to the topic in a very short amount of time, like you would have seen on the title. And today's topic is all about logic gates, PN junctions, diodes, transistors, and logic gates. So all of this in the short and sweet session with me, Shreyas, your physics master teacher. I have been training kids for a very long time after I graduated from NIT Nagpur and did my research from IIT Bombay. And I'm sending lots and lots of kids to the top-notch institutes in the country. And I'm pretty sure you too want to do the same. So if you want to do the same, guys, make sure you hit the subscribe button, stay tuned on the channel, and keep watching all the awesome content for JEE, and that too in English. And to show your love and support, you know what to do. Go ahead, smash the like button down there. So let's begin. All right. Now we all know everything around us is made of atoms. Atoms is made of protons, electrons, and neutrons. Electrons keep going around the nucleus in different orbits, and each orbit might even have a certain amount of subshells. If you take the example of sodium, it has the following electronic configuration: 2 electrons in 1s, 2 electrons in 2s, 6 electrons in 2p, and the 3s is half filled, and the 3p and the orbitals above are not at all filled. Now these are the energy levels of a single sodium atom. But when 2 or 3 or 4 or 5 more sodium atoms interact with each other, these energy levels start splitting depending on how many ever interactions occur. So if there are 3 sodium atoms, you will see the 1s energy level will be split into 3 lines, same with 2s, 2p, 3s, and so on and so forth. If there are 5 sodium atoms, it will be split into 5 lines. If there are 1000 sodium atoms, it will be split into 1000 lines each for each energy level for each orbital. Now, because over here 1s was completely filled, the 1s energy level in the combined form is also filled. Here 3s was partially filled, so the combined energy level when multiple sodium atoms are interacting with each other will also be partially filled. If this is unfilled, this will also remain unfilled. Now what happens is, when multiple sodium atoms, or in general any number of atoms, interact with each other, splitting their energy levels, and if there are too many in number, these energy levels are so close to each other that they look like a continuous energy spectrum, and that is when they are called as bands. So this is the band of energy. That means any electron in the 1s orbital in this atoms which are a part of a solid, you will see that can have any energy varying from here to here. An electron in the 2s orbital can have any energy from here to here. So there is a range of energies which is called as the energy band, and each band has different ranges, and from one band to the next band there is some gap which is also referred to as the band gap, because that's the gap between the energy bands. Based on what kind of bands are formed, you can classify them into 2 types: the filled bands and the unfilled bands. Like you can see in the previous one, these are completely filled orbitals. That's why these bands are filled. This one is not forming a complete pair. It is an empty or partially filled band. So that's why the energy levels above this are unfilled bands. Now the one which is the topmost or the highermost filled band is called as the valence band, and the lowermost unfilled band is called as the conduction band. Electrons inside the conduction band are responsible for the conduction of electricity because they are readily available, they are easily plucked out from the higher energy levels, and they can easily flow, constituting the current. So an electron might jump from here to here and contribute in the current. And that's why this energy band gap is of particular importance, because when an electron needs to jump from here to here, you need to know this energy, because this energy tells you how much energy you need to give to an electron so that it enters into the conduction band zone. And that energy can be provided in many ways. One such way is thermal energy. All these diagrams right now that you see is at 0 Kelvin. There is no agitation, there is no kinetic, rotational, vibrational energy. But the moment these molecules, atoms start vibrating, translating, rotating, twisting, and so on and so forth, they collide and they knock out the electrons and send them to higher energy levels, like the one shown over here in this animation. Right now, there are free electrons on the higher energy level, but you can see at very low temperature, these electrons were in the valence band. Slowly they start jumping as you agitate them or provide thermal energy, and that's how these electrons are available for conduction. So usually at room temperature, you should have few electrons in the conduction band so that it behaves like a conductor. So guys, remember that at absolute zero temperature, no electron will have any energy to jump from the valence band to the conduction band. It is only at room temperature or moderately high temperatures that these electrons jump to higher energy levels to contribute in the electricity. Now, based on how these bands are placed, you have three different types of materials. One is an insulator, where the band gap is so high that an electron from valence to conduction band needs to make a big leap, big jump. It needs a lot of energy to enter into the conduction band. So you will see at normal temperatures, the temperature energy is not enough to make this electron jump from here to here. So there is no conduction and no electricity. That's why they are called as bad conductors or insulators. In semiconductors, which has conductivity less than the conductor but more than the insulator, it's somewhere in between, you will see the band gap is typically low, somewhere close to 1 electron volt to 2 electron volt. So the electrons can easily jump from the energy provided by the thermal energy. Whereas in case of conductors, you will see the conduction band overlaps with the valence band. There is no energy band gap, because of which the electrons can easily transit even without any temperature. That makes it a very good conductor, and that's how the electrons can easily flow, because they are readily available in the conduction band. More specifically, we will be talking about semiconductors in this chapter. Like you can see that the energy band gap for a semiconductor is typically close to 1 electron volt to 2 electron volt, and no electron can reside over here. It can be here or here. That is why this is called as forbidden, because you are not allowed to place the electron here or here or here. It can only lie in these energy zones. So to conclude, semiconductors actually behave like an insulator at 0 Kelvin because there are no electrons in the conduction band. It's only at higher temperatures or room temperatures that they actually show some conductive properties. You will also see semiconductors have resistance slightly higher than the conductors but lower than the insulators. You can also talk about conductivity. Conductivity of semiconductors lies between the insulators and conductors like iron, gold, silver, copper, aluminum, etc. You will also see one interesting thing about semiconductors. When you increase the temperature, more electrons will jump to the conduction band, so it will become more conductive, or rather the resistance decreases, which is exactly opposite to that of a conductor. You remember, conductor, when you increase the temperature, the resistance increases. But for a semiconductor, as you increase the temperature, the resistance actually falls down. Now, to talk about how the conduction of electricity occurs in a semiconductor, you should understand that any semiconductor is made of a fabric of multiple atoms, and each atom forms a covalent bonds with its neighbors. Like shown over here, each silicon atom is forming 4 covalent bonds with its neighbors. So there are electrons which are shared. Now, as these silicon atoms vibrate, translate, rotate, twist, etc., these bonds keep getting broken, like the one over here. So the electron is freed. Similar bonds can be broken at some other places. So you can see some vacancies are created. Those vacancies are basically called as holes. They behave or act like a positive charge because it's an absence of electron. Now, this electron which is freed might roam around and it might enter this hole. This electron which is freed over here might roam around and fill this hole. You will see at any given point of time, there are some electrons going here, some electrons going here, some holes going there, some holes shifting from there to here. So there is an equal amount, an equilibrium is maintained, so the net current will be 0 unless you connect a battery. The moment you connect a battery, you will see the electrons and the holes keep flowing, and that is what constitutes the current. So this is how the flow of electricity occurs in case of any semiconductor. Now the semiconductor's conductivity properties can be definitely altered. So there are multiple types of semiconductors. You can classify it as intrinsic, extrinsic. Extrinsic can be further categorized as p-type and n-type of semiconductor. Let's start with intrinsic. Intrinsic example is silicon or germanium. In an intrinsic semiconductor, you will see that it is made of a pure fabric of either silicon or germanium like atoms. There is no adulteration, you do not add any doping element, and you will see the conductivity is decent in amount. You will see, for example, silicon will make 4 bonds with the neighboring silicon atoms. This will make 4 bonds with the neighboring silicon atoms, and so on and so forth. That's how the fabric has been viewed. And this is where you will see the number of electrons being present is equal to the number of holes being present, because every time a bond breaks, an electron is free and a hole is also created. So the number of electrons and the number of holes are equal in number. The next type is obviously extrinsic type, where you add something because of which the conducting properties changes, and that material which is added is called as the doping element or the doping material. The doping element can be of 2 types. That's why you have 2 categories. The first one is called n-type. Like you can hear over here that it is n. N means like negative. So negative comes from an electron. So basically you add something which has a pentavalent impurity. So the valence shell has 5 electrons. Out of those 5, 4 electrons form bonds with the neighboring 4 silicon atoms. There is one extra electron which is left out. So that extra electron contributes to the extra flow of the current and increases the conduction property. So if you add many such pentavalent atoms, you will see many extra electrons being present which contribute to the extra growth in the current, thus increasing the conduction properties. So the electron concentration is larger than the hole concentration in a n-type of extrinsic semiconductor. The exact opposite is true for p-type. P means positive. Positive can be found by removing an electron, that means hole. So you need a trivalent impurity or a doping element or material to be added. So like aluminium can form a bond here, here and here, and you will see there is one vacancy created. So there is no extra electron because there are only 3 electrons in the valence shell. So that's why you will see there will be a hole created. So the hole concentration is much larger than the number of electrons present there. So the hole is in need of those electrons which are roaming around. So it always tries to acquire those electrons and thus increases the conductivity of the semiconductor. So that's P type of semiconductor for all of you. Now, depending on how many holes and how many electrons are there, there is a very beautiful formula relating these two. So in intrinsic semiconductor, I told you the number of holes and number of electrons are equal. That concentration of holes or electrons is called as Ni. So Ni is the intrinsic concentration of the charges, be it holes or electrons. Nh and Ne are the number of holes or electron concentrations in p-type or n-type. They are related by this formula. Number of electron concentration into hole concentration is number of intrinsic charge carriers whole square. I also told you that whenever you have any semiconductor, both electrons and holes participate in the flow of current, right? So the conductivity of such a semiconductor where there can be some holes, some electrons is given by Ne mu plus Ne mu, where N is nothing but the number of electrons present per unit volume, that is the electron concentration, is the electron charge. Mu is called as the mobility. You might have heard that term in current electricity, which is drift speed by electric field. Plus, here you can put N or you can even put P. This is basically the number of hole concentration. You can put P or you can just put NH, it's up to you, into electron charge or proton charge into the mobility. Again, mobility is nothing but the drift speed, the speed with which the flow occurs upon the electric field which is applied to create that flow. Because only when you apply electric field will the charges move, or else they will just maintain equilibrium. Like you can see, there is a plus term over here. This just tells you that the total conduction is because of both electrons as well as the holes present inside any semiconductor. Now you might be wondering what will happen if I take a p-type and a n-type and I keep them together. So p-type has excess holes, n-type has excess electrons. So if you obviously combine them together, the excess electrons will immediately jump onto the p side, right? So that's exactly what happens, and that's what makes something called as the p-n junction. So you will have a p region with excess holes, and you will have n region with excess electrons as compared to the holes. The moment you make this kind of a semiconductor which has unequal concentrations of n and p type, what you will see is the electrons from the n type immediately jump towards the p type, thus creating a flow of charges, that is the electrons from n to p. So the current actually will be flowing from this side to this side, because current is the flow of positive charges, remember. This process of electrons diffusing from here to here creates a current called as the diffusion current. So a diffusion current is created from p to n type because of the electrons flowing from n side to p side. Electrons are negatively charged. The moment the n electrons flow to the p side, you will see the negative charges and the positive charges created here now creates a potential difference. This is at higher potential because this is positive, because electrons have left it, and electrons getting accumulated creates a negative charge, negative potential or lower potential. So there is a potential difference. This potential difference is called as a potential barrier, because this potential difference prevents more electrons to flow from here to here. Because the electric field is towards your left side, the electric field is towards the left side, any electron trying to reach here will have to face the consequence of the electric field. The force because of the field will be towards the right side because it's a negative charge again. So that force will prevent the further flow of electrons. So there is a barrier created that is called as the barrier potential. This zone is called as the depletion zone, where you will see that the charges are getting accumulated already the moment you create the p-n junction. That's called as the depletion zone. Now in the depletion zone also, remember, there will be some charges which will always be formed because always there will be some bonds broken. So in this region, the moment a bond is broken between any such semiconductor atoms, those electrons which are freed will immediately experience a force towards the right side, because remember there was electric field here, the force will be towards the right side. So these electrons which will be freed at any given point of time will be forced towards this side. This process is called as drifting, and the current produced by that is called as the drift current. So the electrons or the negative charges go from the p side to the n side, so the current flows from n to p side. This drift current is exactly opposite to your diffusion current, and because of this you will see that because both these currents are opposite, when there is nothing else connected to it, both these currents cancel each other and the net current is just zero. Such a p-n junction is said to be unbiased because there is no net flow of charges. There is an equilibrium which is formed. This equilibrium can be disturbed by biasing it. Bias means you create some partial behavior. So you connect p to positive, n to negative, that is called as forward bias, p to minus and n to plus, that's called as the reverse bias. The moment you connect p to positive, you will see these electrons will get pulled over here easily and they will be thrown from this battery and they will be pushed back over here. There will be a good amount of flow of current in such a case, and that is called as the forward biasing. In forward bias, you will see a decent amount of current flows after the barrier is broken. Remember, there was a barrier. So the moment you break the barrier, there is a sudden jump of the current and it allows the flow of the current in the forward bias. And that main current is flowing because of the diffusion current, because these electrons go from here to here. That process is called as diffusion. In case of reverse bias, where p is connected to negative and n is connected to positive, you will see the positive will pull these electrons here and this negative will hold these holes over here. So it will not allow the electrons to flow from this side to this side. Very few charges might just end up leaking from here to here, and it's only because of the minority charges carriers, because of which a small leakage current flows. So the moment you connect it in reverse bias, a very, very small current, often called as the leakage current, is going to flow in the circuit. It's as good as nothing. And that's why you see a very beautiful graph of current versus voltage. The moment you apply any voltage above the barrier voltage, you will see a decent amount of current flowing through the circuit in forward bias. In reverse bias, this current is very, very small. It's called as the leakage current. It's negligible. But only after a very large voltage, the breakdown occurs, and then you will see a sudden jump in the current, but the voltage does not change beyond a point in the reverse bias. This is of particular use in the next point, which you will see, which is called as a Zener diode. Now there are many applications of PN junctions. Now first of all, you should realize just by looking at the graph that the current can only flow in the forward bias, but in the reverse bias, till the breakdown occurs, hardly any current flows, because the current can only flow in one direction. That device is called as a diode. So diode allows the flow only in one direction and blocks it in the other direction. The symbol of the diode is this one. You show a triangle. The triangle points in the direction of the allowed current. It's like a one-way traffic, and it blocks the traffic on the other side. Okay, so this is how a diode looks like in reality, and a PN junction makes it a diode-like working. There are many types of diodes, and there are many applications, like LED is a light emitting diode. So you will see when current is passed through it in forward bias, light will be emitted out of it, and most of your mobile screens and TV screens are made of LEDs. The other application is a photodiode, where light falls onto it, and then you see how the conduction properties change depending on the intensity of the light. Like you might have seen, there are sensors which are placed near the wash basin. The moment you place your hands and you try to wash, automatically the sensor senses that there is less light falling. It triggers the circuit and it opens the wall, and you will see water falling on your hands. So that makes use of photodiode. It is usually used in reverse bias mode to increase and improve the sensitivity of the intensity of light. There is another application, and that is the solar cell, where you don't need biasing. In fact, that is going to act like a battery. The energy from the sun in the form of photons or radiation is used by these electrons in the PN junction, and they jump from one side to the other side. That constitutes the current. So the current will start flowing the moment light energy is going to fall on it. Another application of a PN junction is a Zener diode. Zener diode looks very similar to a normal diode, very small. The symbol for that is slightly different. You just twist the arms over there, and it is always used as a reverse bias and generally used for voltage regulation, because in the breakdown region we just saw that the voltage never changes no matter what you do. So when you use it in the reverse bias, you will see a Zener diode acts like a fixed voltage output. So it is used to regulate the voltage whenever there are fluctuations in the voltage. There is another use of diodes. You might have definitely used chargers or adapters like this. They basically convert the AC current into the DC current. That process is called as rectification. So diodes can be also used to convert AC to DC, basically as a rectifier. There are two major types of rectifiers. One is half wave and full wave. So imagine this is the AC signal, positive cycle, negative cycle, positive, negative cycle of AC signal. If you just take this as the output and you do not give this as the output on the other side, you will see that half of the cycle only is coming out. Here there was positive, negative cycles. Here you just have the positive cycles. That means the current is only flowing in one direction. That means you have converted a bidirectional current into a unidirectional current, and only half of the complete wave is given out. That's why it is called half wave rectifier. Alright, so this is obviously a little bit lesser efficient, because half of the energy, half of the wave is just purely getting wasted, and that can be achieved using diodes like the one over here. This is a AC transformer. When the current goes like this, the diode will allow the current to flow. Okay, so in the positive cycles, the current will come out. But the moment the cycle is reversed, you will see the diode will block the current and no output will come out. So that's why you will see, although the AC has bidirectional flow of current, the output has only unidirectional or just plain DC current. The other one is full wave rectifier. So you even take the negative cycle and flip it on the other side. So you are making use of the complete cycle's energy to be rectified into DC signal. So the entire wave is converted into DC. That is why it is called as a full wave rectifier. So the diagram for that is basically something like this. You make use of two diodes. In the positive cycles, this diode allows the current to flow. This diode blocks it. In the negative cycle, this diode allows the flow of the current, and you will see both the diodes in each of the half cycles allow the current. That way the entire wave is getting rectified. So the bidirectional current converted into unidirectional DC current. The next thing is the transistor. Transistor is nothing but a three-terminal device. So usually in a diode you have P and N material. In a transistor you have PNP or NPN kind of materials, and that creates a variety of new applications. So inside the transistor you can have one side as N, the between maybe P, and the other side as N, or you can even have P and then N and then P over here. These three regions are called as emitter, base and collector. You will see the base is sandwiched between the emitter and collector. The collector is largest in the area, emitter is decently sized, base is very, very thin. But the number of charges in the emitter is the highest, base is the lowest, the doping in collector is moderate as compared to emitter and base. What is the symbol of a transistor? The symbol of a transistor is like this. If it is a NPN transistor, where this is emitter, this is base, this is collector, this is how you show the transistor, and make sure that the arrow mark points outwards for a NPN transistor. This is a symbol. But if you have a PNP transistor, then you will see that the emitter, base, collector, the arrow mark between the emitter base points inwards. That's the way in which you're going to identify the difference between a NPN and a PNP. So for a NPN, the arrow mark is outwards. For a PNP, the arrow mark is inwards. All of them have emitter, base and collector. The characteristics are very, very similar. Whatever I have told you over here, who is doped more, who is doped less, it's all identical. Just that instead of N, it is P, or instead of P, it is N. Now, how do you connect such a transistor? There are three ways of connecting it. Either you take a base which is common and connect it to two circuits, or you take the emitter which is common to both the circuits, that is called as common emitter, or you take the collector which is common and connect it to both the circuits. No matter which arrangement you choose, always ensure that the emitter base is forward bias, no matter which type of transistor it is, and you ensure that the base collector always is in reverse bias for standard functionality. Now, when you talk about the working principle of a transistor, you will notice that in the standard biasing, the electrons from the emitter, they will go to the collector. A very few of them will go through the base and they will come back. Most of the electrons go through the collector and again come back inside the emitter. So what you will see is the emitter current bifurcates into collector current and the base current. That's the reason why emitter current is said to be base current plus the collector current, also the Kirchhoff's current law. Also, you will notice if you change the current of the base by a small amount, the ratio of collector and base or emitter and base being fixed, you will see any small changes here will affect the collector and indirectly the emitter current by a large amount. So small change here creates a large change here, because the ratio of the charge flowing or the currents is the same, and those ratios are given by alpha beta. So alpha is the collector current by emitter current, beta is the collector current by the base current. Very easy to remember, beta and B are together. These ratios being same, you will notice anybody makes a small change here, there is a big change here. And because collector change, if it is large, you will see the emitter current will also change by a large amount. This principle is used for a transistor as an amplifier. Amplifier basically amplifies the signal, it expands the signal, it increases the amplitude. So if you have a small signal, small voltage, small current, you will see by the time it comes out of the collector or even the emitter, you will see the amplitude would have increased. That's the functionality of an amplifier, increasing the amplitude. That's what you will see in most of the audio systems or mic systems around you. And the gain of an amplifier is basically the output current by the input current. Here the emitter is common to both the circuits. So output is the collector current, so IC is on the top, and the base current will then become the input current. That was transistors. Moving ahead to analog and digital signals. I hope you are enjoying this video and you have smashed the like button and also subscribe to the channel. All the signals around you are of two categories. They can have as many values as they want, that is called as analog signals. But if the signal is in the form of high, low, yes, no, true, false, 5 volts, 0 volts, alright, so that is binary kind of voltages, then it is called as a digital signal. Now most of the things around you, the computers, the calculators, your mobile phones, they all work on not analog but digital signals. That is ones and zeros, highs and lows, trues and false, yes and no's. This yes, no, 0, 1 is enough for these machines to understand what data is being transmitted, what calculations are being done, and there are obviously certain amount of calculations which needs to be done on all these ones and zeros. So much of processing is happening on your motherboard, on all your processors, in every device that is there around you. Now because there needs to be some amount of processing, each of these processors fundamentally is one of these few logical elements. These most elementary fundamental logical blocks are just called as logic gates. They are as simply put or, and, nor, not, NAND. These are the most fundamental operators in case of this machine level language or digital signals. The first one being called as a NOT gate, it's a logic. So the NOT gate is symbolized like this with a triangle and a dot, and mathematically you put a bar. So when I say NOT, it means if my input is a yes, the output is a no. If my input is a no, the output is a yes. So this is called as the truth table. So input is 0, output is 1. You can also replace it with false, true, no, yes, hello, hi, whatever you want it. And when the input is 1, the output is 0. So that is basically a NOT gate. There is another gate called as a OR gate. This or this. Basic English, same thing applied over here in these logical circuits. False or false is a false in this truth table. Either this or this. Oh, this is true as a whole. This is true or this is true. Yes, this is true. So true. Either one of them is true. Yes. So that is also true. So that is a OR gate. The symbol for that is a curved D, and you can see these two curves are over here. And mathematically you put a plus symbol over here. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. So 1 plus 1 is not 2 because these ones and zeros are digital symbols. Similarly, you will have a NOR gate. Whatever output you got from OR, exact opposite by putting a dot. So you can see the symbol difference. This was OR, you put a dot over there. It's basically knotting it, basically negating the output. So wherever you are expecting 0, you will get a 1, and wherever you are expecting 1, you will get a 0 because you are negating the output. So you will see this guy's truth table for a NOR gate is exactly opposite of the OR gate's truth table. Then the next gate that you have is the AND gate. So this and this, the symbol for that is a D proper, and a mathematical symbol for that is a dot. So 0.0 is 0, 0.1 is 0, 1.0 is 0, 1.1 is a 1. So that's a AND operator. Only if both are true, then the output is true. Even if one is true, the output is not true. The last one over here is a NAND gate. It's just an extension of an AND gate. You put a NOT over here. So whatever you are expecting, just negate it. Just put a NOT gate in front of the AND gate. You will see that 0 NAND 0 will be 1 and 1 NAND 1 will be 0, because this is exact opposite truth table of the normal AND gate. This NAND and this NOR gate are also called as the universal gates, because using these two gates you can make any other gates by some or the other combination. Now that you know the symbols, there is also an important rule of thumb, or you can say theorem, which can be useful for solving problems. That's called as the De Morgan's theorem or law. So when you have A dot B bar, this is like NAND of it. Okay, this is a NAND gate. That is same as saying A bar plus B bar. Also, when you have A bar dot B bar, when you have A bar dot B bar, that's the same as saying A plus B whole bar. It's very easy to remember. So when you have a dot, split it up, convert the dot into plus, and this bar, you separate it out on both these inputs. Over here as well, you can see the same thing happening. When you have A plus B whole bar, that plus you convert it into dot, that's multiplication or ANDing, and that entire bar you split it up on the two individual inputs. So that's your De Morgan's law, useful for solving problems. Make sure you join the Telegram channel. That's where you're going to get the entire PDF and you'll get all the updates of the upcoming sessions. I hope you enjoyed this session. Do not forget to leave a comment on how you loved this session, and make sure you put on your headphones and keep listening to this session. Even if you don't want to watch it, you can keep listening to it in your free time, and that's how you're going to revise all the concepts. And it's even better if you download the PDF and keep adding your additional pointers in the notes. That's it from my side. This was Captain Shreyas. Thank you for liking and subscribing. See you again. Bye bye. Hasta la vista.